In the Russia-Ukraine war, a significant shift is unfolding in the long-range strike arena. Yet many overlook it because the change is not about a larger explosion, but about how weapons approach their targets. In major strike waves, UAVs often move in first to pull air defense systems into a dense reaction cycle, and only after that defensive rhythm is stretched do the heavier strikes begin to appear. Behind that operational pattern lies a very practical constraint. Ukraine does not have a deep stockpile of cruise missiles to sustain layered attacks at the same intensity as Russia. So where exactly did that boundary once stand? And why was it considered so clear that confusion seemed impossible? If that dividing line is now fading, where are the most visible signs of its disappearance on the long-range battlefield? Join military force as we take a closer look. Before Russia's full-scale invasion of Ukraine, drones and cruise missiles sat in separate boxes in most military thinking because they followed different rules of control, cost, and speed. A cruise missile was designed for a planned route to a fixed aim point, so cruise-loaded coordinates, launched from air, land, or sea, and relied on onboard guidance to fly fast toward the target. After launch, there was little tactical flexibility in real time, which meant the weapon either survived air defenses long enough to deliver a heavy warhead or it did not. Traditional drones worked in the opposite direction because an operator could steer, search, and wait. And that flexibility made drones useful for reconnaissance, decoys, and opportunistic strikes. The trade-off was performance, since most drones were slower, carried smaller payloads, and were more exposed to jamming, weather limits, or interception if they lingered. That division shaped long-range planning because missiles were treated as scarce, high-impact assets, while drones were treated as cheap platforms that could be risked in larger numbers. From 2025 to 2026, both sides pushed designs that blurred those categories, and the change came from engineering choices that moved drones toward missile behavior. Long-range drones adopted stronger propulsion, more autonomous navigation, and tighter flight planning, so they could cover greater distances at higher speeds without constant operator input. At the same time, modern cruise missiles absorbed features once linked to drones, including improved sensors, better terrain, hugging profiles, and the ability to accept updated routing to avoid defended corridors. Some newer missiles use onboard imaging to recognize a target area, reducing dependence on a single set of coordinates. Others can receive updated waypoints during flight, enabling reroutes around radar coverage. Those functions once sounded like drone advantages, but they are now in missile design. These upgrades mattered because air defense is a timing contest in crowded skies, and a target that can change altitude, route, or exposure window forces defenders to treat classification as uncertain rather than routine. The blurred line also changed strike economics, since a force could apply repeated pressure with systems cheaper than classic missiles but more damaging than earlier long-range drones. It also helps explain why Ukraine set ambitious production goals for long-range systems, because sustained deep strike requires a steady pipeline rather than a few headline launches. This shift forces planners to rethink deterrence, inventories, and pace of adaptation. In practical terms, drones and missiles are no longer separate boxes on briefing slides, because the most important systems now sit in the middle and borrow traits from both ends, which sets up the next section on how mass raids stress air defenses. Russia has increasingly treated long-range strike as a production problem, where the goal is not one perfect blow, but a repeatable pattern that can be run often. Instead of betting on a single weapon type, its planners stack different threats in sequence, so the defender has to solve several problems at the same time. This approach also helps Moscow manage risk, because even if the most expensive weapons are intercepted, the cheaper layer can still force disruption across multiple cities and regions. A clear example came on February 3rd, when Ukraine said Russia launched about 450 unmanned aerial vehicles and 71 missiles in one night. The numbers matter, yet the more important point is what those numbers force the defense to do minute by minute, across sensors, command links, and stocks of interceptors. Such raids are designed less as isolated events and more as rehearsed stress tests for the entire defensive network, probing how long it can function under sustained pressure. When a large wave of drones arrives first, air defense crews must keep radars active, track many objects, and decide which ones are decoys and which ones carry warheads. Each decision consumes scarce resources because interceptors are limited, crews get tired, and command posts cannot sustain maximum alert for long. The first minutes of a raid often become a sorting problem, with multiple tracks at different altitudes, speeds, and approach lanes, and with little time to verify what each one is. Drones fit this opening role because they do not need a high hit rate to succeed. They succeed if they pull attention in the wrong direction, reveal where sensors are, and stretch the defense into a constant cycle of detection and response. In practical terms, this first layer is about tempo, because it sets the pace of the whole engagement and pushes defenders into rapid, imperfect choices. That is when the second layer becomes dangerous, because missiles arriving after the drone wave exploit a defense that is already busy. Missiles fly faster and usually carry heavier payloads, so they become the main destructive tool once the protective screen is stressed. The aim is to create gaps that are small in time but large in consequence, such as seconds when a radar is saturated, a battery is reloading, or a crew is forced to choose between two sectors. Those gaps are hard to see from outside, yet they can decide whether a missile reaches an energy node, an airfield, or a logistics site. In this environment, uncertainty becomes a weapon, since defenders cannot afford to ignore a track, but they also cannot afford to shoot at everything. Commanders then have to balance protection of critical infrastructure with the need to preserve interceptors for follow-on waves, which can arrive again before resupply is complete. Even when many incoming targets are shot down, the defense still pays in fatigue, maintenance, and depleted stocks. Radars that radiate for long periods face wear and increased exposure, while launch crews must reload, reposition, and stay ready for a second night with little recovery time. Over time, that cost changes behavior, because commanders may hold interceptors for later or shift coverage to protect the most critical sites, leaving other areas more exposed. This is the deeper effect of layered raids, because they do not only seek physical damage. They also seek to control the defender's decision cycle, so the defender is always reacting, often late, and uncertain about what the next wave will contain. It has a political effect, because repeated alarms pressure leaders to explain outages and losses and to spread scarce air defense systems wider, which can thin coverage where it is needed most. If Russia can run saturation as a routine, then the side facing it must solve a different problem than simple interception. It must find ways to disrupt the raid before the layered sequence takes hold, which is the question that drives the next section and sets the stage for examining alternative strike models. Ukraine faces a structural constraint in long-range warfare that shapes every strategic decision it makes. Unlike Russia, it does not possess a vast stockpile of cruise missiles that can be used repeatedly over months without fear of rapid depletion. This limitation means Kyiv cannot sustain a high-intensity pattern of combined strikes in which drones open corridors and large numbers of missiles follow to deliver decisive blows night after night. Even when Western partners provide advanced systems, those deliveries are finite and often influenced by political debates outside the battlefield. As a result, Ukraine must think in terms of efficiency and tempo rather than sheer volume of fire. Long-range strike becomes a matter of managing scarcity while still attempting to impose pressure deep behind enemy lines. This scarcity forces military planners to weigh each launch not only for tactical value, but also for its impact on future operational capacity. Relying solely on earlier generations of long-range drones exposes two clear weaknesses. The first is speed. A slower platform spends more time in contested airspace, which increases the likelihood of detection, tracking, and interception. Modern air defense networks rely on layered sensors and shared data links across regions. The longer a drone remains visible to that network, the more opportunities defenders have to position interceptors or apply electronic countermeasures. In a dense defensive environment, time itself becomes a liability. The second weakness is payload. Many long-range drones were designed for precision strikes, yet their warheads are smaller than those carried by cruise missiles. Even if such a drone penetrates defenses, it may damage a facility without generating the broader disruption needed to affect logistics, industrial output, or energy distribution. Deep strike is not simply about hitting coordinates on a map. It is about creating cascading effects that stretch repair capacity, force resource reallocation, and generate uncertainty far from the front line. A limited payload can achieve symbolic success, but it may fall short of altering operational balance in a sustained way. This creates a strategic dilemma for Ukraine. It must reach deep into Russian territory to impose costs, yet it cannot rely on a narrow stream of expensive missiles, nor can it depend on slower drones that struggle against reinforced defenses. The challenge, therefore, is not only firepower, it is campaign rhythm. To influence the wider war, strikes must arrive often enough to complicate planning on the other side, while remaining affordable enough to continue over time. Consistency matters as much as intensity. Without repetition, even effective strikes risk becoming isolated events rather than instruments of strategic pressure. This is why Ukrainian planners have placed emphasis on expanding domestic production of long-range systems. Producing at home reduces dependence on external supply cycles and allows design changes to be introduced more quickly. It also supports a model in which losses can be absorbed without halting future operations. The objective is to create a class of weapon that travels faster than traditional drones, carries a more substantial payload, and remains less costly and less politically constrained than imported cruise missiles. Such a system does not need to match the most advanced Western missile in every technical detail. It needs to balance speed, range, destructive capacity, and manufacturability in a way that supports sustained pressure. In this context, the shortage of cruise missiles is more than a shortage of hardware. It is a shortage of operational tempo. Without enough long-range missiles, Ukraine cannot shape the battlefield at depth in a consistent manner. Innovation, therefore, becomes a strategic requirement rather than a preference, because redefining available tools is the only way to restore a sustainable rhythm to deep strike operations. The emergence of the drone missile hybrid represents a direct response to Ukraine's deep strike dilemma. Faced with limited cruise missile inventories and the constraints of slower long-range drones, Ukrainian designers began to search for a system that could bridge the gap between the two. The objective was not to replicate a classic cruise missile, nor to simply modify an existing drone, but to combine selected strengths from both into a new operational class. These hybrid platforms are built to travel faster than earlier long-range drones, using stronger propulsion and more advanced navigation to reduce exposure time in contested airspace. They also rely on greater autonomy, which lowers the need for constant operator input and reduces vulnerability to electronic interference. In effect, designers aimed to shorten the time between launch and impact while maintaining enough flexibility to adapt to changing battlefield conditions. This approach reflects a shift from improvisation toward structured innovation in long-range strike doctrine. Speed and low-altitude flight together alter the balance between attacker and defender. A faster object reduces the interval between detection and engagement, and when that object travels close to the ground, radar coverage becomes less consistent. Low-altitude flight is not merely about avoiding sensors. It forces air defense units to process data under pressure, often with only seconds to classify the target, assign an interceptor, and coordinate guidance. In modern networks where multiple systems share information, even brief hesitation can create exploitable gaps. The hybrid concept seeks to compress the defender's decision window to its minimum. This tactical compression increases uncertainty at the command level, because operators must choose quickly whether the track represents a minor threat or a major strike asset. Such ambiguity is part of the design logic. At the same time, payload capacity has expanded beyond that of many earlier long-range drones. Hybrids are engineered to carry larger warheads, raising the destructive potential of each successful penetration. While they may not match the largest cruise missiles in raw power, they approach a level where damage can extend beyond a single facility and disrupt broader infrastructure. This combination of speed, autonomy, and heavier payload reshapes how deep strike missions are planned. The Palyonitsia system is frequently referenced as an illustration of this development path. It shows how Ukrainian industry is experimenting with higher velocity profiles, low-altitude routing, and integrated guidance in a compact configuration. However, the broader significance lies not in one platform, but in the pattern of design priorities now emerging. Hybrids are meant to occupy the space between traditional cruise missiles and standard drones, giving planners more flexibility in selecting tools for specific targets and corridors. They can be deployed as part of layered strike packages or used independently when a balance between cost and impact is required. This intermediate layer expands operational choice without eliminating older systems. Cruise missiles still retain advantages in range and power, while conventional drones remain useful for reconnaissance and saturation roles. The hybrid approach adds a structured middle option that aligns with Ukraine's resource constraints and strategic objectives. It reflects a practical adjustment rather than a symbolic breakthrough. By compressing reaction time, increasing per-strike impact, and maintaining relative affordability, these systems help Ukraine sustain pressure despite inventory limits. They do not replace existing tools. They redefine the space between them, offering a more adaptable method for matching speed, autonomy, and force to the demands of a prolonged conflict. Cost and production capacity sit at the center of any prolonged conflict, especially in deep strike campaigns that rely on repeated launches over time. Hybrid systems offer a clear advantage in this area compared with traditional cruise missiles, because they are built with more practical components and less complex manufacturing chains. Western cruise missiles such as the Tomahawk are widely reported to cost several $1 million per unit, reflecting advanced guidance systems and specialized materials. These weapons provide precision and range, yet they require long lead times and stable supply arrangements. For a country under constant pressure, dependence on small batches of expensive missiles can create operational pauses. Hybrid platforms aim to reduce this vulnerability by lowering the unit cost and simplifying production requirements. When a system is more affordable, commanders can plan operations with the expectation that some losses are acceptable rather than catastrophic. This financial flexibility changes how often deep strike options can be considered. Production scale is as important as price. If components are easier to source and assembly processes are streamlined, output can increase even during wartime disruption. Domestic manufacturing reduces reliance on unpredictable foreign deliveries and shortens the time between battlefield feedback and technical improvement. That tighter cycle supports consistent planning because planners can estimate future availability with greater confidence. Lower cost combined with higher output also allows for more frequent launch windows. Instead of saving a limited number of missiles for rare, high-profile events, Ukraine can consider patterns of pressure that extend across weeks. The focus shifts from a single dramatic strike to sustained operational strain. This approach aligns with the broader goal of influencing logistics, infrastructure, and decision-making beyond the immediate frontline. The economic logic of hybrids naturally supports swarm tactics. A swarm does not rely solely on numbers, but on the ability to generate simultaneous pressure across multiple approach routes. When unit cost decreases, launching several systems at once becomes realistic rather than symbolic. The objective is not always immediate destruction of every defended site. It is to maintain persistent strain on defensive networks. Each incoming track demands radar attention, communication coordination, and the possible use of an interceptor. Over time, this steady demand can erode readiness and increase maintenance burdens. Air defense depends on balancing sensor coverage with missile stocks. If defenders must fire frequently, they either replenish rapidly or accept thinner protection in selected areas. Swarm tactics exploit this tension by creating more simultaneous decisions than can be handled comfortably. Even when many systems are intercepted, the defender still pays in ammunition, labor, and operational focus. This cumulative pressure influences higher-level planning. Commanders may be forced to prioritize certain regions while accepting risk elsewhere, which gradually reshapes the strategic picture. Modern conflict increasingly revolves around the relationship between cost and effect. A system that delivers steady disruption at a sustainable price can shape the war more effectively than a rare weapon that delivers spectacular impact once. Hybrid platforms are built around this principle, enabling deep strike operations designed for endurance rather than singular moments. Unpredictable flight profiles complicate adaptation for air defense systems. Unlike slower drones or classic cruise missiles that follow relatively stable patterns, hybrid platforms can vary speed, altitude, and routing in ways that reduce the value of standard classification models. Air defense networks rely on rapid identification to assign the correct interceptor and engagement method. When a target does not clearly match a known profile, the defender must decide under uncertainty. That uncertainty can delay response or result in the use of less suitable resources. In tightly connected defense grids, even small changes in trajectory or timing can disrupt coordination between radar stations and launch units. This does not create disorder, but it introduces friction, and friction under time pressure can open narrow windows of vulnerability. Hybrid systems are designed to exploit those windows by compressing the interval between detection and impact. When altitude shifts and routing adjustments occur during approach, defensive planning assumptions lose reliability. As a result, adaptation becomes reactive rather than predictive, and each engagement requires renewed assessment instead of routine procedure. The defender must constantly reevaluate threat libraries and engagement thresholds, which increases cognitive and operational strain across the network. This operational challenge is intensified by the speed of technological change within the conflict. The war has accelerated a cycle in which new strike systems are deployed, evaluated in combat, and modified in short intervals. Data from interceptions, electronic interference, and flight behavior feed directly into updated designs. Drone missile hybrids are products of this rapid refinement process. They embody a strategy in which continuous adjustment is treated as a central element of military planning. For defenders, this means that countermeasures must evolve just as quickly, demanding constant retraining and system recalibration. Strategically, the significance of this dynamic lies in persistence, rather than dramatic success rates. Even if only a portion of incoming systems penetrate defenses, incremental gains in speed, payload, and cost efficiency accumulate over time. A single successful strike with higher destructive power can produce wider infrastructure effects than earlier platforms. Meanwhile, lower production costs allow repeated launch cycles without exhausting available inventories. The outcome is sustained pressure on targets deep inside Russia, which compels defensive forces to remain in a state of extended readiness. In such an environment, the decisive variable may not be one individual weapon. It may be the capacity to force air defense networks into compressed decision windows where hesitation or miscalculation becomes increasingly likely. The boundary between drones and cruise missiles has shifted from a clear dividing line to a continuous spectrum, and the hybrid layer now occupies a practical center within that spectrum. Russia relies on large-scale combined raids to disrupt defensive rhythm, while Ukraine must pursue a form of deep strike that aligns with its available resources and industrial capacity. In this environment, the drone-missile hybrid is not simply a new piece of hardware. It represents a strategic adjustment aimed at sustaining long-term pressure beyond the immediate battlefield. By blending speed, automation, and relative affordability, these systems seek to maintain operational momentum even when success rates are limited. The central forecast is clear. The next phase of competition will revolve less around maximum range and more around adaptation speed. The side that shortens its development cycle and optimizes the balance between cost and operational effect will hold the initiative in long-range warfare. If this report helped you better understand how modern warfare is evolving, stay engaged not for spectacle, but for awareness and critical thinking. War is shaped by technology and strategy, yet its consequences are human, which is why informed discussion matters more than ever. Subscribe to Military Force for clear, fact-based analysis that informs, questions, and supports responsible conversations about security, conflict, and the path toward peace.